In section 1.8, we want to talk about indexed sets. So let's consider an example to begin with. Let's say I've got a bunch of sets. A starts with 1, then 2, 3, all the way up to 10. B starts with 2, and then 3, 4, all the way up to 10. C starts with 3 and goes up to 10. 4 starts with D and goes up to 10. Maybe I want to keep going, so I'll have another one that starts with 5, another one that starts with 6. Right? And maybe I don't even want to stop at 10. Maybe I want to stop at 100. So I could have 100 different of these ones of these sets. At some point, I'm going to run out of letters. Right? So for this sort of reason, we might want to have a better name for our sets. So instead of calling these sets just A, B, C, what I can think about is calling them specific names, especially names that will give us some information about that set. So I can call this A1, and that would be a nice name for it because it's going to start with that 1. And then I can call this next set A2, and this next set A3 and A4. Right, so I'm not really changing any of the information I have. I'm just using better names for my sets that give me some information. Sometimes these names will give me specific information about the set, and other times they'll just be helpful names so I can refer to a whole bunch of different sets at once without having to use too many different letters. So these are called indexed sets, and this little number next to them, that's the index. Okay, so what can we actually do with indexed sets? Well, if I have a lot of sets all together, I might want to be able to take the union or the intersection of these sets. All right, so I can say I can do A1 union A2 union, keep going, all the way up to A sub n. So we're just going to assume that we're going to use all of the numbers in between there, up to n, all of those positive integers. And we know that the union has to be in one of those, an element in the union is in one of those sets. So what I can say is that this is going to equal the set of x, such that x is in A sub I. So that way I can refer to all of my sets at once, just as A sub I, for at least one I, right? To be in the union, it has to be in one of the sets with, we'll say that I is between, there's an inequality here, 1 and n. So this is going to allow me to refer to this whole collection of sets, right? A whole set of sets, so we usually call that a collection, at once. Now I can also do that for the intersection. In order to be in the intersection, instead of just having to be in one of the sets, it has to be in every single one of the sets. So I need that x to be an AI for all I with I between 1 and n. Right, so we can still refer to this union and this intersection now for these greater numbers of sets. So let's look at an example. I'm going to have my A sub I be the interval from I to 5, the closed interval, and we'll do that for I equals 0, 1, all the way up to 5. So I'm defining what A0 is, A1, A2, all the way up to A5, all at once. And then I can say, okay, what is the union of A1, A2, and A3? So I can write this out. A1 is just going to be the interval from 1 to 5. I'm unioning that with the interval from 2 to 5. And then I'm unioning that with the interval from 3 to 5. So I'm taking my closed interval 1 to 5, unioning with that with my 2 to 5, and then unioning that with my 3 to 5. So the union is going to be just that interval from 1 to 5. Right, so, careful here. I made a mistake. I accidentally drew an intersection. Let's change that. So I wanted to just have all of these symbols be the same symbol. So as we're going through, it's important that we don't mix our symbols, because if I did mix those, then I would have to be careful with using my parentheses. If I just have a whole bunch of unions all in a row, I don't need to be careful about parentheses because I have this associativity. But if I don't, then I need to know which order I should do things in, so I would need those parentheses. So I meant for those to both be unions there, so we can make that fix. Now, we can also do this for intersection. So if I want to intersect A1 through A5, I'm going to intersect the intervals from 1 to 5, 2 to 5, 3 to 5, 4 to 5, and 5 to 5. We can define this interval, right? This is just going to be x less than or equal to 5, less than or equal to 5. So that interval now is going to just be the set containing 5. Sorry, that intersection is the set containing 5, because that's the only element that's in each one of these, because that's the only element that's in this last one, which happens to be the smallest. So by using this index set, it just allows us to talk about much more general sets. Okay, so building up from this, we're going to recall some notation that we've used previously, and then from there we'll build up new notation for unions and intersections. So maybe you remember seeing from Calc 2, when we're talking about infinite sums, we can use this sigma notation or this summation notation. So a big sigma, again, if you're trying to LaTeX this one won't come up as much, but you can just use \sum. And I'm going to go from here, I'll use I as my index. So I equals 1 to n, because I n to n. And then the thing I'm adding is just I. So I can use that big sum so I don't have to write out each of my terms. If I have something more general like this, I am going from A1 up to AK. So I can say I'm adding from I equals 1, that's the first one, to K, that's my last one, of A sub K. So just kidding, I'm not using A sub K each time, that was my index. Each time that index matches the number on the bottom, so that should be an A sub I. Okay, so I plug in I equals 1, I get 1. I equals 2 gives me A sub 2. I equals 3 gives me A sub 3. I add those all together, and I stop when I get to that K. So inspired by this, we can actually use the same thing for unions and intersections. So I can say the union from I equals 1 to 3 of AI, and that's another way of writing A1 union A2 union A3. Or I can say the intersection from I equals 1 to 3 of AI, and that's just going to be A1 intersect A2 intersect A3. And then you can start and end these anywhere that you want. A little note on LaTeX here, when we're using these symbols, if you want to get this big union symbol, remember the union symbol is that cup. So the LaTeX is just big cup. And then for this one, you use big cap. And then if I want to get the stuff underneath it, I just do underscore. So maybe write this so that we can make sure we can see it very clearly. So we've got big cup, underscore, and then I want that whole I equals 1 to be under. So I put that in braces, so that whole thing goes under. And then we can put a caret, and the stuff that here will go on that caret. So caret 3. That'll give us this symbol. If there's more than one thing up in the top, you can put that in braces to make sure it knows to put the entire expression up there. All right, so here's our first discussion question for this section. I'm giving you 3 sets, A1, A2, and A3. And I just want you to find the union from I equals 1 to 3 of AI. And then the intersection just from I equals 1 to 2. So not all of 3 of them. I'm going to go ahead and post these Jamboard slides for these in advance. So if you'd like to go ahead and get your solution written up on these slides in advance, you're welcome to. You can find that in the Google Drive folder. Okay, now with that summation notation that you've seen before, you've seen that you can do infinite sums and infinite products maybe, but we can also do infinite unions and infinite intersections. So, right, my A sub I here is just going to be some indexed collection of sets. This is sort of a notational thing. Whenever I have a set of sets, I call that a collection. So a collection is just a set of sets. So my A sub I is going to be some indexed collection of sets. The index is because it has that I there. So maybe, for example, here we want our A sub I to be the sets of natural numbers where that natural number is less than I. So I can figure out A sub 1 would be the natural numbers less than 1, A sub 2 would be all the natural numbers less than 2, and so forth. Now I can talk about the union from I equals 1 to infinity of A sub I. Right? I can have infinitely many of these sets because they're indexed by those natural numbers. So I can take this union, that's going to be A sub 1, union A sub 2, union A sub 3, but it's going to keep going for all infinitely many of those sets. So that's going to be the set of X such that X is in AI for some I greater than or equal to 1. So for some index greater than or equal to 1. So here, right, note our convention is, if I don't explicitly say what set I'm pulling from, when we're using this sigma notation, the index set, the set of allowed indices, so the set of things that this I is allowed to be equal, is that natural numbers. So I can talk about things like A sub 1, A sub 2, right? A sub any n, where n is a natural number. But right now, we can't talk about A sub pi, A sub negative 1, right? I can't even talk about A sub 0 unless we actually explicitly say that we're going to start at 0. So that's the only one that's okay sometimes. And that's just our general convention. But these guys are usually not going to be good. We're not going to want to have those in our index set. But we'll see towards the end of this section that we can expand that if we want to. Okay, next here, I can think about this intersection, right? So I have A sub 1 intersect A sub 2 intersect A sub 3. Again, it's going to go on for infinitely many times, so I need to be more specific about what that means. So that's going to be the set of X such that X is in A sub I for all I greater than or equal to 1. Again, where that I is coming from my index set, which by convention is going to be n, unless we say otherwise. Okay, so we have that down here as well. The index set is going to be that set of natural numbers, unless we're explicitly told otherwise. Okay, so let's try some of these. I know that this union from I equals 1 to 3 can be written as A1 intersect A2 intersect A3. Those are the ways, I drew a 3, we've seen before. But we can also write it in this new notation where we say explicitly that I is one of the elements of the set 1, 2, 3. So instead of saying, okay, well, we're just going to assume it's an integer and it goes from 1 to 3, I can explicitly write the index set. So that's just the set of possible indices. And that's going to mean the same thing. So it's just a different way to write this notation. Now if we have the union from I equals 1 to infinity of A sub I, that's just telling us that I'm getting all of those natural numbers as my indices. So I could write that as the union over all I in those natural numbers of this A sub I. So we could be more explicit about what our index set is there. When we're really explicit about our index set, then we can allow for bigger index sets. So for example, I can have the index set where that's coming from the set of all real numbers. So that's just going to be the union over all a sub a, where a can be any real number. So the union, again, is just going to be the set of x, such that x is in a sub a for some a in that index set. Now, when we're doing these indices, we usually like to use I or k or n whenever that's going to be some natural number. And then we like to use things like a or maybe x or y if that's going to be a real number. So that just sort of helps the reader know exactly what kind of variable we're thinking about here. So I switched to an index of a for that real number. I could have also used x or y. A is a really good general one. So here I have this general index set I, and if I'm taking the intersection, I'm just going to be thinking about the set of x, such that x is in a sub a
for all a in I. So since it's an intersection, we have to make sure it's in every single one of those elements of our index set. So x has to be in every single one of the big A's, no matter which big A we have.
So we can really get general sets here. Right, so these are kind of weird. We'll do a couple examples, but here's an example where I might want to have my index set be the real numbers. So I can think of the set of x in R such that, gotta make sure I use the right index here. Let's fix that. X is greater than a. So then write a sub 2 is just the set of x such that x is greater than 2. And that's the set of x in R, so that's just going to be the stuff from 2 to infinity. A sub pi, that'll just be from pi to infinity. A sub a half will be from a half to infinity, and so forth. So I'm allowed to have any real number here as my starting point. So this set of sets, this collection, is indexed by those real numbers. Okay, let's go through some examples here. So if I want to find the union of all sets of the form A cross 0, 1, where A is going to be allowed to be any real number. So before we get into this, let's just try some examples to get a feel for what this set looks like. So I'm allowed to pick any real number I want for an example, and so I can think about what this is. So when A equals 1/2, I get a half cross 0, 1. So geometrically, if I want to picture this, I can picture the first coordinate as just that set that only has 1/2 in it. The second coordinate is going to be this whole set 0, 1. So I end up getting that Cartesian product is any point of the form. So this is going to be a set where the first coordinate is a half, the second coordinate is some real number, where that real number is between 0 and 1. Okay, so that's what my first set looks like. We should color code that here. That's that guy. But then if I did something like A equals 0, then I'm going to get 0 cross the interval from 0 to 1. So that's going to be this line here, that set. I could have A equals a quarter, and I'm going to get a quarter cross 0, 1. So that'll be somewhere here. All right, so we're going to get all of these different lines above these different A values, but my A is allowed to be anything in R. So if I think about that whole union, then I should end up getting anything between 0 and 1 here. So my union there over all real numbers, where the first coordinate is a real number, and then the second coordinate is a number from 0, 1, is just going to be r cross 0, 1. Because if I take anything in this set, it's going to have an x in the first element, where x is an r. It's going to have something from 0 to 1 in the second element, and each of those is going to appear in one of the sets in this union. So definitely take some time, think that over. And you can ask any questions you have on it in class. Let's do one more example here. So if I do the intersection from over A and R of the same set, A cross 0, 1. Now I'm going to be intersecting these different sets. So again, if I think about some examples here, when A equals 1/2, I'm getting that set that has a half as the first coordinate, and then x as the second, where x is between 0 and 1. And then when A equals 0, I'm going to get the same thing, but the first coordinate is 0. So we have to ask ourselves, is there any overlap between these two sets? And we can think about it, right? One of them is here, the other is here, up in our picture from before. So there's no overlap, which means that this intersection is the empty set. Okay, so here's a question for you guys to think about. What is the union of all x, where x is an element of the power set of n? So as you're thinking about this, you maybe want to write out some of the elements of the power set of n. You obviously can't get all of them, but you might want to think about what that is and think about unioning all of those sets together to figure out what this union is going to be. All right, so let's do one final example. This one's kind of a tough one, so make sure you're ready for it. We have a special case here where I have J is some set that's not empty, and it's a subset of I. So I'm just going to go ahead and just pre-draw a picture here. So I'm going to have a J set sitting inside an I set.
So we want to show that the union of all alpha in J of A sub alpha is a subset of the union of all alpha in I of A sub alpha. Right, so in this first union, I'm just including the things that are inside the index set J. In the second union, I'm including the things that are inside I, and I want to show that I get that subset. So we've seen before how to show subsets. So what I'm going to do is I'm going to take X as an arbitrary element in the union over all alpha and J of A sub alpha. Since it's in that union, we can write out what that means. That means that X is in A sub alpha for at least one alpha in that index set J. Now we're trying to show that this element is also in the union over all alpha in I of A sub alpha. So what I really want to know is that it's in one of the A sub alphas for the alpha in I. But I know that alpha is in J. Well, J is a subset of I. So since J is a subset of I, if alpha's in J, then alpha is in I. And we know that it was in J, so that means it's going to be in I. So maybe here we can say, since this is true and I know it was in J, right? It wasn't if it was true, it actually wasn't true, then alpha was in that I. Okay? So that means X is in A sub alpha for at least one alpha in I, the same alpha that was in J. So my X is in the union over all alpha in I's of A sub alpha. So we're just really unpacking these definitions and showing something in one set is also in the other set. That's how we show these subsets. As a final question, we have here two statements similar to the last one. So again, I have J is not the empty set. J is a subset of I. And I want you to look at these two statements, they're about intersections, and see which one is true and why. So as one of your weekly challenge problems, if you'd like, someone can present this in class. So you don't have to do a write-up of it, you can just explain which of these is true in class, and then you'll get your points for the week.